Funding for this program is provided by Annenberg CPD to advance excellent teaching.
What can psychology tell us about where the processes of the mind are located within the structure of the human brain? From visual perception and imagination to how we evaluate social groups. Cognitive neuroscience, this time on Discovering Psychology. In 1848, one man's misfortune began psychology's long journey into the mystery of the human brain. Phineas Gage, a railroad worker, suffered a catastrophic injury while preparing to blast bedrock. The iron rod he was using to pack the gunpowder blasted through his skull and tore away the front part of his brain. Remarkably, Gage never lost consciousness and was even able to joke with the doctor when he arrived. After a few months, he seemed to recover his health fully, but he was no longer Gage. Hostile, impulsive, unable to control his emotions or his obscene language, Gage lived 13 more years with this new, disturbed personality. With this celebrated case, psychologists began to connect brain injury with changes in behavior. They could begin to map where the processes of the mind were located within the human brain. But the study of the brain through injury is a slow process. So psychologists have developed a number of tools to measure the brain functions of normal people. Electroencephalogram recordings, or EEG, record brain waves with scalp electrodes. Event-related potentials, or ERP, can record brain waves during specific cognitive events. Computer-assisted tomography, or CAT scan, can show the brain's structure. Positron emission tomography, or PET scan, was first to image the brain in action. But a new tool introduced in the 1990s goes one step further. Functional magnetic resonance imaging, or fMRI, can show the brain at work in high resolution. For the first time, psychologists can see the mind's functioning deep inside the physiology of the active brain in normal people. When our brain is active, it uses up the oxygen supply in that area. This momentary depletion is followed by an oversupply of oxygen rushed to the site. This alters the magnetic qualities of the blood, a change recorded by the scanner. After further computer processing, a detailed picture of that local brain activity emerges. With new brain imaging technology, psychological scientists can explore far more about our abilities than ever before. From better-known systems like perception to less understood systems like motivation and emotion. Perhaps our most awe-inspiring ability is how we see the world. Vision is so complex, about 40% of our brain is devoted to it. Decades of human and animal studies have revealed what is happening in the early stages of vision. Light energy converted to neural signals travels from the retina to the thalamus. Then these signals move to the back of each hemisphere of the brain, to an area called the primary visual cortex. It is this area that researchers are beginning to explore with fMRI. David Heeger has studied some of the specialized functions of this visual center.
Of the neocortex, pretty much the back third is involved in some way or another with visual processing. The primary visual cortex, which is also called V1, is the first receiving area in visual cortex that receives that information coming from the eyes through the thalamus, and that's right along here and rolls over a little bit onto the backside right there. And from there, the neural signals fan out to a whole bunch of other visual areas of the brain.
In fact, there may be as many as 40 distinct visual areas in the cortex of the brain. And some of these visual areas record what we see almost photographically, a process called retinotopic mapping. Animal studies show how this works. In a monkey brain, visual neurons were chemically treated to turn dark. After seeing this wheel-like pattern, the monkey's brain recorded the image, seen here in a section of its visual cortex. This representation of the physical world is the starting point for further visual processing.
So, as I'm looking out here in front of me at some object, I need to know a lot of things about that object. I need to know how far away it is. If it's hurtling toward me, is it small enough that I can reach out and catch it, or do I have to duck and get out of the way? I might want to know something about what color it is, whether it has a texture on it or not.
With fMRI, Higa can observe visual processes at work at the back of the brain.
Here we're going to look at an example of how different areas of visual cortex are specialized for different kinds of visual functions. On the top, you're seeing a flickering checkerboard here that's alternating with a blank gray screen, and a pattern of randomly positioned white dots that are first moving, then stationary. The bottom two panels are showing visual cortex responding. On the bottom right, in response to the flickering checkerboard, you see activity in V1, primary visual cortex. On the bottom left, you're seeing activity in the same place, but you're also seeing activity here in the right hemisphere and over here in the left hemisphere, visual area MT, that's very specialized for visual motion processing.
The visual areas funnel information to two higher processing regions. The parietal cortex helps us determine where things are in space, so we can grab, duck, and navigate. And the temporal lobe helps us to determine what kinds of objects we are looking at. Nancy Kanwisha of MIT is studying a portion of the temporal lobe where we recognize a high-priority object, the human face.
What we usually see is a little patch of brain in the back in the right hemisphere. Mine is right about in there someplace on the bottom surface of the brain, that produces a much stronger signal when the subjects look at faces than when they look at anything else.
All you need to do is lie there, hold still, real still, and look attentively.
This brain activity occurs across a wide range of faces. Front views, side views, line drawings, cartoon faces, even cat faces all produced a very strong response. But was it really whole faces that were creating this effect, or just parts of faces?
One of the things we've been concerned with is to argue that it really is faces per se that this area responds to, rather than, say, two little dots, or curvy lines, or other kind of simpler descriptions.